All right, guys. So today I want to go over a really quick work through of what the optimal angle is to throw a projectile to maximize the distance that it goes. Right. So how should I throw a ball to get it to go as far as humanly possible? And of course, for a problem like this, we're going to have to assume a few things. We're going to have to assume that the initial velocity is constant. So in the case of you throwing a tennis ball, let's say, we're going to assume that you can throw with the exact same strength, no matter how high or how low or how horizontally you throw it. So depending, no matter what angle you throw it at, we're assuming that you can throw it at the same exact speed. Okay, so if you look over here to the left, I have a few, examples of the different ways in which you can throw a ball, right? And just to go over the significance of the idea of an angle of a throw, the angle essentially refers to the angle at which the initial velocity vector is at, right? The angle at which the first throw was made. The angle at which the first vector was at. So if we're looking at these, it looks like this. So as you can see, this is the smallest angle, this is the second smallest angle, and this is the largest angle, right? Okay, so now some of you might intuitively have an idea of where you would want to throw it, but you don't really know mathematically. Or better yet, I wouldn't say you don't know, but I would say you'd have to be able to prove it mathematically, right? And this is something I struggled with as well. I knew that I had to throw it at somewhere in the middle, right? I knew if I throw it too high, if I throw a ball like this, it's just gonna come straight back down. And if I throw a ball like that, it wouldn't quite make it to the very end. So I knew it's somewhere like in the middle, but where exactly? Is it 30 degrees? Is it 60 degrees? Is it 45 degrees? I really didn't know. But let's try to use our intuition and our understanding of kinematics in general, of two-dimensional kinematics, to tackle this problem. So first of all, let's use this one equation that I think is the most useful for this kind of problem. So let's use the equation that says the change in x equals the initial velocity times time plus 1/2 at squared. All right, so, well, in this case, right, we got to think about a better way to put it would be this. We have our change in x here. Our question is, how do we maximize this? Right. So how do we maximize this? Well, if we look at the right side of this equation, we have these two parts, I guess you could say. You'd have to maximize both of them, right? Or maximize one at a faster rate than the other, sort of thing. That's really, really complicated. We have time here, we have acceleration, we have our initial velocity. So our initial velocity, we know. That we know, okay? Because we're assuming that it's some value, right? It's like, 4 meters per second. Your hand can throw it at X meters per second. Doesn't matter. You can shoot a gun at some X meters per second in the air. Okay. But we don't know what the acceleration is. We don't know what the time is. That's the most difficult part. And we also don't have any of these things in terms of an angle, right? We just don't. So one way you could try to tackle this problem is by making a few assumptions. First of all, one of the assumptions we can make is that acceleration is equal to 0, since in the x direction we're assuming there's no wind. Oh yeah, of course, we're also assuming this is a perfect situation, right? Where there's no air molecules, we're sort of in space, right? There's no air molecules, there's no resistance against the object in the x direction, but we're not technically in space because we do have Earth's gravity acting on us as if we were on the Earth's surface. So imagine you have a mini little space simulator or vacuum on the surface of the Earth, okay? So our acceleration in the x direction is 0. Okay, so if we make that assumption, this entire term goes to 0. So now we're left with the change in x is equal to v initial t. Well, what's v initial in the x component? Well, that just equals v initial times cosine of theta. Because if we have some vector, the x component, right here, I should do that in yellow. The x component is simply v initial comma x. This is v initial total. And then you can say that cosine, and this is obviously theta, Cosine of theta is equal to v initial x over v initial. Therefore, v initial in the x direction is equal to cosine theta times v initial. Okay, so we can then write over here that the change in x is equal to v initial times cosine theta. I should say v initial x actually here, just to keep things consistent and also to make them more truthful, I guess. Times t. Okay, so now we have v initial, that the vector, times cosine theta times t. Okay, so now we have this. But again, we don't have t, right? We're trying to think about how to maximize the projectile irrespective of time, really, right? So we can't have time in there because we don't really care about time. We don't care how long it takes for it to go the furthest possible. We care about what angle it takes to get the furthest possible, right? So if you were to just look at this equation as it stands, you'd think your first intuition would be, well, v initial is constant, time is not constant, if that's the issue, but cosine theta can just be maximized, and we know that the cosine maximum is 0, right? At cosine of 0 angles, or theta equals 0, at cosine of 0, the cosine of 0 is equal to 1, right? And then that's the maximum value it can achieve. So we'd assume that a theta of 0 is equal to 1. And that's not really true. And you can think of that intuitively. If you just throw a ball horizontally, that isn't the furthest you could throw it, right? So we got to go a little deeper into this problem. So let's try to use the other component, the y component, to help us try to solve this problem. Let's think about what the y component looks like using this kinematics equation. Vy initial times t plus 1/2 a t squared. Let's zoom in on this real quick. Now, I'll try to figure out a few things. Change in y, let's try to simplify this. What's Vy initial? Well, with the same reasoning over here, it's just the sine theta component instead of the cosine theta. So we can say that this is equal to V initial times sine theta times t plus 1/2. Well, what's a in the y component? A is always just g, right? It's just g, and we should actually say it's negative g, because we're going down, right? Acceleration due to gravity is always downward, slowing things down. Okay, so we got minus 1/2 g, and then again t squared. And now here is the very interesting part, the very, very interesting part. No matter what, whenever I throw a projectile, at the end of it, its initial y position, let's say, was 0. Where is it going to end up? Well, it's going to end up at 0. So let's use the fact that the change in the y, the displacement in the y direction, is equal to 0. Well, if we do that, this looks like this. 0 is equal to v initial sine theta minus 1/2 gt squared. We can rearrange this to say 1/2 gt squared is equal to v initial sine theta. Now, what can we do with this to help us with this equation? How can we relate these two things? What can we do? Well, we can realize that the thing that we're trying to get rid of in the top equation and for the x displacement is time. Well, if we solve for time over here, we can plug it back in and see what we get from there. So let's do that. Let's solve for t over here. Oh, I'm missing a t in all these equations. Sorry about that. It's right there. There we go. Okay. Now, let's solve for t. Well, first, if I divide by t from both sides, this cancels out, that cancels out, and we get 1/2 g is equal to v initial times sine theta, and t still left over here on this side. Now, if I just set t is equal to v initial sine theta divided by 1/2 g. Or you can also write this as 2v initial sine theta over g. Now we can plug this back in over here. And we can write change in x is equal to v initial cosine theta times t. Well, what is t? Well, let's just go ahead and plug it straight in. Change in x is equal to v initial cosine theta times 2 v initial sine theta over g. Alright, so things are looking very, very complicated. I agree. Right, so far things look weird. But let's try to simplify it as much as possible. Well, we have this v initial over here and this v initial. That gives us v initial squared times 2 cosine theta sine theta divided by g. And now here's where we can use a very, very interesting fact. We can use the one trigonometric identity that states that 2 cosine theta times sine theta is equal to sine of 2 theta. Okay? So this is a very, very helpful trig identity, which, again, like if this was on some physics exam in your, class in high school or university, you wouldn't be expected to know this. At least I hope you wouldn't be. But of course, there's some professor out there who's going to expect that you know all of your trig identities. But nonetheless, this is a very helpful one in this case. So I'm going to plug this in to our equation. And we can get the change in x is equal to v initial squared times this entire part, right, just became sine 2 theta. And then just divided by g, which is a constant. Okay? Now let's ask ourselves, what angle would give us, using this equation, the largest possible x value, or displacement value, right? The most distance traveled in the x direction. Which value? Well, in this case, this is constant. This is constant, right? G is just equal to 9.8 meters per second squared. V initial is just some constant, right? How hard you throw it. It doesn't really matter. Well, the change in x really is just proportional. Proportional to sine of 2 theta. So what's the max? What's the max that sine 2 theta can achieve? Well, sine in general is, I'll write a different color. This is getting a little not neat. So sine is largest at 1. Sorry, not at 1. It's largest at 90 degrees, which gives you the value of 1 in the unit circle. So when is sine of 2 theta equal to 90 degrees? Or better yet, it's not really what sine of theta is equal to 90 degrees. It's when is 2 theta equal to 90 degrees? Well, that's when theta is at 45 degrees. Which, if I were to post this picture up, this is basically a pre-done image of all of our work. Or better yet, what our work would look like if you were to input different angles into our equation right here. Let's see if this thing loads. My computer is acting very slow. There we go. Right? So this is exactly what you would expect given these equations. 45 is the one right here. This line going like this. Oops, what's going on? Alright. It's 45 is this line going like this. And notice how it goes the furthest because, again, if we were to input our 45 into this equation right here, this is what we would expect to get. Let's make this a lot smaller. This computer is really not good at handling this kind of stuff. Alright, let's see what happens there. Okay, yeah, well, this equation right here. Oh, you gotta have a G here. that equation right there is the final equation you would need to solve this problem, and my computer is literally dying, but that's fine. I'll just put this right there. Okay, yeah, the video's over at this point. You guys can just click away. This is pretty cringy to watch. But I'll be getting a new computer soon. But you guys got the point. This is the general idea behind how you would solve that kind of a problem.